wanted to give you a few more examples with solving trig equations. Notice that I've filled in a lot of these solutions already on this page. So I'm going to post this whole worksheet filled in for you so that if you want to practice some problems and check some solutions, if you've got questions about those things, you can ask those. Just wanted to give you another, pardon me, another outlet to practice some of these problems and then see the solutions. But I wanted to work through some of them on this video so that you could get a little bit of an explanation to go through some of them. So we talked about using identities to help us with rewriting equations so that we can actually solve it. Here's an example of this. So we have 3 secant squared x minus 2 tangent squared x minus 4 is equal to 0. I don't have the same trig function in both terms there, so I'd like to convert one in terms of the other. And we remember that we can write secant squared as 1 plus tangent squared. Now I have everything in terms of the same trig function. Distribute that 3. So we get 3 plus 3 tangent squared x minus 2 tangent squared x minus 4 is equal to 0. If we simplify, this gives me tangent squared x. I have a minus 1, so I'll move it to the other side as a plus 1. And then take the square root of both sides. Now, in this particular problem, they ask you to find all the solutions in the interval from 0 to 2 pi. So I just need to go around and see in which quadrants I can find angles where the tangent is equal to either plus 1 or minus 1. In quadrant 1, that's pi over 4. In quadrant 2, that's 3 pi over 4. In quadrant 3, that's 5 pi over 4. And finally, in quadrant 4, that's 7 pi over 4. So we get those 4 solutions that are in the interval from 0 to 2 pi. But again, one of the reasons why I wanted to show you this particular problem is because of the replacing of a function with an identity, one of the terms with an identity, so that we get all of them in terms of the same trig function. So the two that you'll use, well, actually there's probably 3 that you'll use quite often. You've got your Pythagorean identities, which we used here, but also don't forget the sine of 2x. Just break it up as 2 sine x cosine x. That's one of them we'll use. Another one is cosine of 2x. There's 3 of these, remember, but the 2 that you will use when you're solving equations will be the 2 cosine squared x minus 1 or the 1 minus 2 sine squared x. And those depend upon whether or not the other term or terms that you see are cosine or sine. That's how you make a decision on which one to replace it with. If the other term in the equation is cosine, you'll use this first one. If the other term in the equation is sine, you'll use the second one. All right, let's go down here and work with these. I changed the directions to all of these to do things in radians. I would rather do radians than degrees because you're taking trigonometry to go on to calculus. All calculus is done in radians. You do not do calculus in degrees. So that's why I changed the directions to all of these to be either interval from 0 to 2 pi or just telling you to do the answers in radians. All right, so this number 7 here. First thing we need to do, isolate the sign. This says the sine is positive root 3 over 2. The angle in quadrant 1 is pi over 3. I'm going to write the general solution first, so I'll write 2n pi. The angle in quadrant 2, that's where else the sine is positive, is 2 pi over 3, and I'll add the 2n pi. So ordinarily, if this were just an x instead of a 2x, we would have the 2 solutions pi over 3 and 2 pi over 3. Okay, but in this, and those would just be my solutions that were in from 0 to 2 pi. But we don't have just an x, we have a 2x. So I'm going to solve, divide by the 2 to get pi over 6 plus n pi. And this would give me pi over 3 plus n pi. So we had 2 solutions to start with. This 2 in front is going to double the number of solutions. We're going to end up with 4 solutions. The way we get those, we plug in 0, we get x is pi over 6, or x is pi over 3. we plug in 1. When we plug in 1, we get pi over 6 plus a pi. So we get 7 pi over 6. We plug in 1 over here, we get a pi over 3 plus a pi. That gives us 4 pi over 3. And I know that these are the 4 that I'm looking for. Again, we would have had 2 originally. This 2 in front doubles it. Another way that I would know that I'm done is if I try to plug in 2 here or here, I get 2 pi. Well, if I take 2 pi and add it to something, I'm outside the interval from 0 to 2 pi. So this is our final solution in this problem. This one asks us that we're going to use our calculators, use inverse functions, use our calculators. So first thing I need to do is factor this thing. So I need to set it equal to 0. Oops. Let's actually set it equal to 0. And let's see if we can factor this. I need what? I need... can I factor? Yeah, I can factor this. So this is 4 tangent theta, and then I need a minus 3 here, and a tangent theta, and a plus 2 here. So I get 4 tangent theta minus 3 times tangent theta plus 2 is equal to 0. We set each piece equal to 0. And isolate. So we have those 2 equations we need to solve. Again, an angle that has a tangent equal to 3/4 is not one we know off the top of our head. Neither is an angle that has a tangent that's equal to -2. So we use our inverse tangent function on both of these. So go over to our calculator. First one was inverse tangent of 3/4. We get 0.6435. So let me go over to here. This one was about 0.6435. Flip back over to our calculator. I also need to do inverse tangent of -2. This is negative 1.1071. So this one's approximately negative 1.1071. Okay, now there's a couple of things that we need to worry about. This problem asks for all solutions in the interval from 0 to 2 pi. This gives me one that's between 0 and 2 pi. It's in quadrant 1. We also need the one that's in quadrant 3. So the other one would be pi plus that. Remember, we have to go find it in quadrant 3 because tangent is positive in quadrant 1 and quadrant 3. When we do the inverse tangent, it only gives us an angle in quadrant 1. So to get the one in quadrant 3, we need to add a pi to it. Over here, they give us an angle in this gives us an angle in quadrant 4, but it's a -1, and we want 0 to 2 pi. So the first thing we need to do is we need to add pi to this to get from quadrant 4, to get from quadrant 4 to quadrant 2. So I'll add a pi, and then I'll also add another pi to get an angle that's coterminal with that original one, but is in between 0 and 2 pi. So these 4 answers here are the answers to the original equation using the calculator. All right, so remember again, when we do this for tangent, the reason I have to add the pi here is because the inverse tangent only gives us one of the angles. It only gives us the one that's in quadrant 1 in this case. We got to go find the other one, which is 180 degrees around from it. That's why we add the pi. This one, we did something similar. We added the pi to get from quadrant 4 to quadrant 2. The reason we had to do another pi on top of it was because I needed to express this angle as an angle between 0 and 2 pi. So I had to add 2 pi to it to get to that, to get the positive number instead of having that negative value. All right, let's see if we've got a couple more down here. Let's look at 16, another one of these where we need to use an identity. I want to get this everything in terms of sine, because I see the sines to the first power, and this one I know something I can plug in for it. So I get 1 minus sine squared x plus sine x equals 1. This just gives me negative sine squared x plus sine x equals 0. We can factor out a sine. And then do the same things we've been doing. Set each piece equal to 0. So we have sine of x is equal to 0, or sine of x is equal to 1. I believe the instructions for this one are find all solutions. So sine is equal to 0 at the multiples of pi. We know that from our knowledge of what the sine function looks like. It crosses the x-axis at 0, pi, 2 pi, and so on, and negative pi, negative 2 pi, and so on. We also, from this one, get sine is equal to 1 at pi over 2, and then we add multiples of 2 pi. All right, let's look at 18. Tangent 3x is equal to 1. So this one already has the tangent isolated for us. Tangent is equal to 1 at pi over 4. That's the angle in quadrant 1. It's also could also be in quadrant 3, but remember the period for tangent is just pi. It's not 2 pi. So I can get all of the solutions by just putting a plus n pi here. Now we can divide by 3. So I get pi over 12 plus n pi over 3. This would be our expression for all solutions. This particular problem asks us for solutions in the interval from 0 to 2 pi. So let's go to town here. I believe we're going to find 6 of them in this case. And the reason why I know it's going to be 6 is because this originally would have had 2 solutions in 0 to 2 pi, because I would have had the pi over 4 in quadrant 1 and the 5 pi over 4, what you get when you add pi to pi over 4, in quadrant 3. So I had 2 originally, and this coefficient here in front of the x is a 3, so I'm going to triple the number of solutions. So when n equals 0, I get pi over 12 plus 4 pi over 12. I'm sorry, plus a 0. That gives me pi over 12. Let me write it as x equals. When n equals 1, I get pi over 12 plus a pi over 3. That's 4 pi over 12 plus another one. So I have x is 5 pi over 12. And notice that we just keep adding 4 pi over 12. We're going to add a pi over 3 every time. So adding another 4 pi over 12 gives you 9 pi over 12, which simplifies to 3 pi over 4. Adding another 4 pi over 12 will give you 13 pi over 12. Adding another one gives you 17 pi over 12. Adding one more gives you 21 pi over 12, which simplifies to 7 pi over 4. And if I add another one, I end up over 2 pi. You would get, what, 25 pi over 12? And 2 pi is 24 pi over 12. So these 6 answers are the solutions to the equation that are in the interval from 0 to 2 pi. Let's look at a couple more here. I think I got 2 more. This one's similar to the last one. It's just there won't be as many. All right. Isolate the sine. Sine is negative in quadrants 2 and 3. The angles that give me a root 3 over 2 would be pi over 3 angles. So in quadrant 2, we have 2 pi over 3. In quadrant 3, we have 4 pi over 3. And then we divide by the x, divide by the 2 and get pi over 3 plus n pi, 2 pi over 3 plus n pi. And let's see what the directions say. All in the interval from 0 to 2 pi. So in this one, let me just give me a little bit of room to work here. We expect to see 4 solutions in this case, because the original would have had, if this were an x instead of a 2x, we would have had 2 solutions. So this 2 in front is going to double the number of solutions. We get those solutions when n equals 0 and n equals 1. When n equals 0, we get the pi over 3 for the first one and 2 pi over 3 for the second one. When n equals 1, that's 3 pi over 3 when I put in a 1 for n. So I get 4 pi over 3 in the first one, and I get 5 pi over 3 for the second one. So those are our 4 solutions in the interval from 0 to 2 pi. All right, last one. This should say equals 0. When this factors, we have tangent x minus 1. Tangent x minus 5 is equal to 0. Set each piece equal to 0. And move things over. I'm going to do 2 steps at once. So I get tangent of x equals 1 and tangent of x equals 5. Now the first one I can do. The first one, if I do tangent of x equals 1, that tells me that x is pi over 4 in quadrant 1. I could put a plus n pi here, but notice this: the directions here are find the solutions in the interval from 0 to 2 pi. The other one's going to be 5 pi over 4. That's the angle that's down in quadrant 3. This one, I don't know an x value that will give me tangent of x equals 5, so I'm going to do the inverse tangent. And if I go to the calculator again, I think I already have that on the screen. Inverse tangent of 5 is 1.3734. So go down here, 1.3734. This, remember, is in quadrant 1. Inverse tangent always gives you an angle in quadrant 1 or quadrant 4. We have found the one in quadrant 1. To find the one in quadrant 4, we need to add a pi to it. So we also get the pi plus 1.3734. So we get these 4 solutions. So again, I'll post all of these solutions on Moodle so that you can see them, so that you get another 26 problems here where you can see them worked out for you. We've got the other worksheet already posted on Moodle as well. Again, for class time, I will use that to answer your questions, so you can log into Zoom on Friday and get questions answered if you have any. Talk to you later.